Right, so we've done essentially 3 lectures so far on Turing machines. The first 2 specifically about Turing machines, and the third one about representations, meaning how one can represent different kinds of data using encodings of the data as words, and then talk about computability with respect to that data, that kind of data on Turing machines. The examples considered in the lecture last week, well, there weren't actually that many, it was mainly the natural numbers and products of natural numbers. There are many other examples of interesting kinds of data to which that technique can be applied, so which one can represent. And you're going to look at quite a lot of those today in the exercise class. So in the exercise class today, you'll see more applications of the notion of representation than we had quite a narrow range of applications of representations last week. What we're going to do in the lectures now for the next few weeks is consider other models of computation, so to speak, other than Turing machines. And that's going to culminate in lecture 6 on the 9th of November with the presentations by you, all on different models of computation. So by the end of the presentations, we'll have seen more models of computation than we'll ever want to see again. Although if I teach the course again, then I'll probably see them all again in the future. But anyway, we will have seen very, very many models of computation. What I want to do, so today's lecture 4, so we've got 2 lectures before that lecture with your presentations. So what I want to do today and next week is to look at one specific other model. And this other model is the computable partial functions on the natural numbers. So we're going to look more at computability on the natural numbers, which now in retrospect we paved the way for last week by talking about representations of the natural numbers on Turing machines. So what we mean by the computable partial function is we simply mean the collection of all partial functions from k tuples of natural numbers to natural numbers that are computable. We had a definition of that last week, what it means for functional k tuples of natural numbers from k tuples to natural numbers to be computable. But this collection indexed over all k greater than or equal to 0. So simply we're going to look at the collection en masse of partial functions of arbitrary finite arity on the natural numbers that happen to be computable. Before going on with this, notice that I've included the case k equals 0 here. I'm including partial functions from a 0 tuple of natural numbers to natural numbers. I'll sort of answer this question later on today, so don't worry about it too much. But just to do your instinct, so to speak, to get you thinking about the right sort of thing, and probably many of you know immediately the correct answer to this. What are the computable partial functions in the case k equals 0? It's kind of clear what we mean when the arity is 1 or more. There's only one sensible answer to what it means when the arity is 0. So in the case k k equals 0. So 0 and 2. So you can think about that, but I'll sort of answer it later. So I said we're going to look at essentially it's a new model of computability, but this doesn't look much like a model of computation. I mean, our model of computation so far, Turing machines, was something very physical, something that we can easily understand in what sense it corresponds to computing an algorithm when we're executing a Turing machine. So in what sense are we addressing that question of a model of computation here? Well, the approach we're going to have today is the following. Okay, that seems... Sorry, I'm just trying to get the camera in the right place. So today, what we're going to do is we're going to characterize this collection of functions in a purely mathematical way, a purely descriptive way, that doesn't look like it has anything to do with computation. Well, I mean, look, you can see something to do with computation. It doesn't look like it has anything to do with Turing machines. So we'll give a self-contained and I would say mathematical rather than computational of the computable partial functions. And when we've done this, what I'm going to claim is that what this gives us is an alternative model of computability. In the sense that, first model of computation, the Turing machine is clearly a model of computation. Using that, we define what it means for a language to be semi-decidable, decidable, for what a total or partial function on words, what it means for it to be computable. And lastly, for a total or partial function on the natural numbers of possibly arbitrary, what it means to be computable. All of that tied down to the model, and with the Turing machines, we therefore have a mathematical model given of computation explicitly, and of therefore the notion of computability. If we do this, if we give a self-contained and mathematical characterization of these functions, of these computable functions, then one can ignore the Turing machines. You can just say, this is what it means for a function to be computable. So that's a new model. Computability is just that, that's modeled by our self-contained and mathematical description of these functions. Of course, actually, the main difficulty here, well, maybe not of course, but I tell you the main difficulty is going to be, it's easy enough to describe these functions in this way. Actually, doing that even predates the notion of Turing machine computability. So people had already identified these as interesting functions, all of which are computable with some sort of model of computability. But the difficult thing is going to be, well, we have then two different notions of computability, one given by Turing machines that gives us a notion of computability on the natural numbers, and another, the direct description. And of course, we want to compare them, and it's going to be the case that they both coincide. And so a major technical difficulty, or the major technical difficulty, is going to be understanding that this is the same notion of computability as that given by Turing machines. And hopefully we're going to cover all of that today. So notice here I'm saying a model of computability rather than a model of computation. I mean, it's not really such a big distinction to make, maybe, but whereas Turing machines are clearly modeling the computation steps, our description here is not going to have explicitly a notion of how one computes and computation steps in it. So I think what we're really modeling here is the notion of computable function independently of how one computes it in some sense. But nonetheless, the descriptions we give here will have a sort of implicit algorithm behind them. So people do also call this a model of computation. Anyway, that's enough background and motivation. Let's get going with the technical side of it. So what we're going to do is simply define a class of partial functions and deem that, or declare that to be, declare is the right word, declare that to be the class of computable partial functions. And we're going to do it in a mathematical way. We're going to say, well, these functions are going to be generated as the smallest collection of functions that contains a few basic functions that we clearly want to count as computable, and is closed under a few operations on the combining functions into new ones that we can see preserve computability. So I'm going to define the computable partial functions in that way. But before doing that, we're going to define a smaller class. So I'm going to use essentially the same methodology to define two collections of functions: a smaller class and then a larger class. And the larger class is going to be all the computable partial functions. So the smaller class, they're called primitive recursive functions. So the primitive recursive functions finality, allowing some unary functions, some binary functions, some zeroary functions, and so on. So F is some collection of partial functions. It's the smallest collection that satisfies some conditions. So it contains the basic functions and is closed under some rules for combining functions. So I'm going to write it as in the notes, satisfying three conditions, 1 to 3 below. So one is that F contains the following basic functions. So it contains the function z, which is a function, which is a total function of zero arity, defined by z of, well, so now I'm partially answering the question I raised earlier. A function of arity k expects a k tuple of natural numbers as its argument. The function of arity 0 expects a 0 tuple of natural numbers as its argument. The 0 tuple of natural numbers is just open and close bracket. So open close bracket is the element, is the unique zero of natural numbers. So we're defining what this function does on its unique argument, and it's z, it's called z because it's the zero function, so it returns the value 0. And then s is the successor function. It's again a total function, and so s, the total function now has a single argument, and the successor function does what its name suggests, it adds 1 to the input. The last one are the projection functions, and we have a projection function. The projection function allows us to project an n tuple of arguments onto its I value, the value of position I. So this is going to go from natural numbers to the power of little n. Sorry, I'm going to change this. I want to be consistent with the notes, so I'm going to change this little n to a k here. These sort of things, if you change them, they can, obviously, it doesn't matter what you call an index, but sometimes one runs into notational problems later. So the idea here is that I don't know why in the literature it's called U, it's a projection function, but anyway, if we give it a k tuple of inputs, x1 through to xk, then it returns it projects on the I index component, so on xi. So the conditions here are to have any x1s to xk's. We do in this case need that k is greater than or equal to 1, and we need, and 1 needs to be less than or equal to I, less than or equal to k. Then that makes sense. Okay, so we're saying it's a collection of partial functions that contains all these functions. Plus, it's going to have to satisfy conditions 2 and 3, but in particular, it contains this zero function, successor function, and these projection functions. Notice that all the functions so far are total functions. So we don't actually have any partial functions in here yet. These are the basic functions. Condition 2 is that it's closed. The functions in the collection are closed into composition. So whenever you have some functions in your collection F, if they have the appropriate arities that you can compose them together, then that composite function is also in the collection F. So 2 is composition. In a circle like that. So if we have one partial function of arity k belonging to the collection curly F, and we have, and in order to compose f, what I want to do is compose f by applying f to some other functions applied to things. In order to do that, well, f takes k arguments. So we, in order to compose f with some other functions, that all these functions only return as the result value a single natural number. So we compose in general with k many functions. So we give it k different functions to compose it. So if we have an f and k different functions, g1 to g1 up to gk, of some other arity, doesn't need to be the same arity, so this is L here. So if all these functions are in f, then the composition, which I'm going to write f composed with g1, tuple of g1 to gk, is also in f. How's this composition defined? Well, in the expected way, but let me write that out. So f composed with g1 to gk. That composite, if you so let me just clarify, that composite function is again a function of arity, partial function of arity L, same arity as the g1 through to gk. So it is also in there. So if we apply, to define this composite function, if we apply it to L arguments, then what we get is f applied to g1 of x1 through to xl as the first argument, g2, well, let's not write the intermediate argument, but that's in dot dot dots, and gk of x1 applied to xl as the kth argument of f. Okay. Right. Tricky, but not very, because I asked a similar question last week. Yes?
All G's have to be the same.
No.
Arity or...
Oh, sorry, yeah, all of the G's have to be the same arity. They're all given arity L, and so we can apply all of them to this L2 here. Yes, indeed. Good. Good question. So my question for you is, I made a similar mistake last week and then pointed it out afterwards. Can anyone see what mistake I've made here? Mistake, in a sense. Sorry?
That's only the whole G.
Right, so again, for this composite to be defined, it will only be defined if all the G functions are defined and f is defined. So indeed, that's part of, so that's related to, so that's correct. And because of that, there's a mistake in what I've written.
The equal sign should be the
equal sign. So once again, neither the right-hand side might not be defined if one of these functions is partial, in which case we don't want the left side to be defined either. So the equal sign needs to be the clean equals. Okay, so this is closure and decomposition. So I'm just underlining, we normally refer to these conditions as by name. I'm underlining the name. So here we've got composition. Here we've got the basic functions condition. And there's one. So we want f to be the smallest collection satisfying 1 to 3. So there's one missing, number 3. And this is a slightly trickier one. In this case, if f is a k argument partial function that belongs to f, and g is a k plus 2 argument partial function, both belonging to f, so then so is, meaning it also belongs to f, so is the partial function which I'm going to call curly R. Oh, actually, let's be consistent with the notes. It's very hard to do fonts on a whiteboard, but in the notes it's sans serif R. So that's a sans serif R. So RFG, this is a function in k plus 1 arguments. So they might look a bit arbitrary. That's a 1, by the way. And this is defined by, we need to say, so we need to define a function of k plus 1 arguments. And this is defined in the following way. So RFG applied to x1 through to xk, that's the first k arguments. And then the point of the last argument is that we're going to give a recursive definition based on the last argument. So if the last argument is 0, we give the base case. And if it's not 0, we make a recursive definition in terms of smaller values of the last argument. So this RFG function on a k plus 1 tuple whose last argument is 0 is simply defined to be, well, again, this might be undefined because f is a partial function, so it's defined to be f applied to x1 through to xk. And in the case that we apply this function RFG that we're defining to a function that's not 0, so any such function can be written as x plus 1. I mean, the number is x plus 1 for this smaller number x. And in this case, well, what we do is we apply g. So f's our function. Where is it? Here. F's our function that we use to define the base case. G is going to be our function that we use to manipulate the step case in our recursive definition. We need to give it k plus 2 arguments. So we apply g to x1 through to xk. The k plus 1th argument is this number, that the number we're calculating the recursive function on -1. So that's just x. The last argument is the recursive call the function. So here is the last argument. We're recursively defining a function, and we're going to call the function RFG now on the smaller value. So we'll decrement the last argument. So by RFG to x1 through to xk and x. That's it. These are the primitive recursive functions. So, smallest collection of partial functions that satisfies these conditions. Now, I'm going to just state a fact as a proposition. It's a proposition in the lecture notes. Let me put it in this corner because it's, I didn't change the board, the camera, so I will. Well, I'll put that there for the video, and meanwhile, write on a different board. Well, somebody can pause that if they really want to. I'm going to put now the fact about partial recursive functions. Sorry, not the partial, what am I saying? The fact about the primitive recursive functions. Oh, come on. So this fact is, so we call a partial function on the natural numbers is called primitive recursive if it belongs to this smallest collection of partial functions that contains the basic function and is closed under composition and I didn't even say the name here. So this function RFG is defined by primitive recursion. So the name for this condition is primitive recursion. This way of combining functions is called definition by primitive recursion. And the proposition is that every primitive recursive function is total. Is a total function. Every primitive recursive function is total. So why is this? Well, the basic functions are total. And if we use this composition operation and we apply it to total functions, f and g's, and by the way it's defined, we also get back a total function. And also if we use the primitive recursion operation, and we again apply it to total functions, f and g, you can see, you can work it out from this definition, a simple proof by induction shows you that once again you get a total function back. So another way of saying that is the total functions, all the collection of all total functions of arbitrary finitarity on the natural numbers is a collection of functions that contains the basic functions, is closed under composition, and is closed under primitive recursion. So since the primitive recursive functions are the smallest, defined to be the smallest collection of such things, is necessarily, the primitive recursive functions are necessarily contained in the total functions. So every primitive recursive function is total. So let me just write that up as a high-level proof. Prove the collection of all total functions contains basic functions and is closed under composition and recursion. Hence, it contains the primitive recursive functions, which is the smallest subclass. Okay, so given this, why did I bother to fuss? Why did I bother to make the fuss about talking about partial functions and using cleaning equality to state the equalities? Because once you're using partial functions, your expressions might be undefined. And the reason for that is that when we come, at the moment we've only got the primitive recursive functions. I want to extend this soon to give us a way of defining not just the primitive recursive functions, but all the partial computable functions. And once we do that, we're going to, of course, have some partial functions because some partial functions are computable. And as soon as we've got partial functions, we need to know how to apply these operations to partial functions. So that's why I'm using this greater generality. If I were just concerned with defining the primitive recursive functions, I could have just made everything total to begin with. Right. So before going to the partial computable functions, and I think the last thing I want to do in this hour, I just want to give you some very simple examples of showing how one uses these conditions to define functions by primitive recursion. And the exercise classes next week will consider some trickier examples. And in fact, next week you'll come to appreciate that primitive recursion is, I mean, these are just, you have very, very simple basic functions, two pretty simple ways of combining functions, but it's actually remarkably powerful. You can do quite a lot with primitive recursion, well, really a lot. And we'll get some flavor of that also later today. But to begin with, let's just do something just to appreciate the definitions. Rubbing some of them off the board here, but never mind. Need the space. So let's define some simple primitive recursive functions. So let's have a function that I'm going to call little f sub 1. And that's going to be a unary function on the natural numbers. So just from the natural numbers to itself, but I'm going to, in any case, write the ariths in here. And this is the function, this is the identity function, f of x equals x. Well, the identity function, was it one of our basic functions? Does anyone know the answer?
Yes.
Yes.
Projection.
Very good. So indeed, it's projection from a one tuple to itself. So f, sorry, I'm calling this little f1. So f of 1, we can define it's certainly a primitive recursive function because it's just the projection u11 from the one tuple to itself. Now I'm going to define g1. And this is the function g1 space. So it takes a three tuple of arguments and it returns the third argument with 1 added to it. And this is also primitive recursive because, sorry, this is g1. g1 is defined as the successor function composed with the function that takes a three tuple and projects it to its third component. So this is S composed with U33. And now I'm going to define H1 to be equal to R F G. So applying primitive recursion to F and G. So let's see what that does. So H1 is then, so F was a function of one argument, G was a function of three arguments. That means K is 1 here. So RFG is a function of two arguments. So this is a function from pairs of natural numbers to natural numbers. And if we look at what it does, well, so H1 applied to X and 0. So that's R. Sorry, I should have said this is R with F1 and G1. So this is, so X and 0, this is F1 of X, of X. So equals F1 of X is X. So H1 of X and 0 is X. H1 of X and let's say Y plus 1 is the second argument. Well, this is, so this is our X, this is our Y plus 1. So it's G1 applied to X, Y, and then H1 applied to X, Y. So it's G1 of X, Y, H1 of X, Y. G1 just takes its third argument and adds 1. So that's H1 of X, Y plus Y. So in other words, just writing this more briefly, H1 of X0, taking out the middle bit, H1 of X0 is 0, H1 of XY is H1 of XY plus 1. I'm sorry, this should be plus 1 here. Okay. Does anyone recognize the fact there's a unique function that satisfies these two equations for all XY? Sorry, I made a mistake. Sorry, that should be X. Yeah. Let's write this more neatly. H1 of X, Y is, sorry, I'm getting it wrong again. So somebody must Sorry? Addition. X plus 0 is x. X plus y plus 1 is the same thing as x plus y plus 1. And these two equations, well, this is true for all x, y, uniquely characterize addition. So, addition is a primitive recursive function. Yay, we can add numbers with our primitive recursive functions. Let's do one more.
Could we have got addition with the plus one in the first component? Would that be a
Yeah, you can.
different definition?
It would be a different definition. Yeah, you can define it to work that way around as well.
But it is still
And then-
addition. So
But it will
it's
still be addition, and in the end, you can prove that your addition is associative, so it's not going to. But there's something. But indeed, so we could have chosen a different definition, and exercise do that.
not completely unique.
No, what is unique is that addition is the unique function that satisfies this.
Okay.
What isn't unique, this is not the only way of defining addition using the ingredients of a primitive recursive function. But nonetheless, this uniquely characterizes the addition function. Anyway, exercise, define it another way around, to work the other way around. So actually, I mean, the thing that makes sense here, the adding one is just the operation on numbers here. So the thing that makes sense is you could define addition to do its recursion in the first argument rather than its second argument. So if you wanted to. But anyway, let's do one more example. So to see that the programming of little functions on the natural numbers, this is kind of like using a very silly programming language in a sense. We're using particular forms of defining, of specifying what functions do, following these rules. So let me just do very quickly, I think it's on, yeah, so let's say, so now we've got an F2, and this is F2 of X. We want to define a constantly zero function. So we can do that by F2 is the composite of the zero function, which is a function of zero arity. So we can compose that with any zero tuple of single arity functions, or it doesn't matter what, but anyway, we just compose that with the zero tuple of functions, and that will give us, thinking of them as unary functions, and that will give us a. So this takes the constant zero of zero arity and turns it into a function of arity 1 or arity 2 or arity 3. This particular shorthand, this particular device.
That should be the power of n b1. The last F2 defines as n on the power of 2. So
It should.
yeah.
Thank you. And again, we're going to define G2, which is on, again, a 3-argument function. And in this case, it's G of X, Y of Z is Z plus X. So we can define that because, so this is G2. So G2 is our H1 composed with projection of 3 arguments onto the third tuple, onto the third argument, and projection of the 3 tuple onto its first argument. And then again, we do H2, we define this to be what we get from primitive recursion by F2 and G2 by primitive recursion from F2 and G2, and this is again a function of 2 arguments. And this one now satisfies, I won't go through all the intermediate things, but it now satisfies H2 of X at 0 equals 0, and H2 of X, Y plus 1 equals H2 of xy plus x. And hopefully you can see that this is the unique function satisfying this is multiplication. Okay, right. Well, it's close enough to 3 that we can restart at 3:15. So that's the end of the first part. If you've got, okay, so we've defined the primitive recursive functions as the smallest collection of partial functions containing the basic functions enclosed under composition and primitive recursion. And having done that, it's now only one step further to define the computable partial functions in an analogous way. And in fact, to properly reflect that we're giving a different definition of the computable partial functions from the one we had last week using Turing machines and the one earlier in the lecture when I said the computable partial functions we write as this collection of functions, I'm going to actually give a new name to the functions defined in this way, which is the partial recursive functions. The definition is, and let's immediately not a good pen. Then the partial recursive functions are the smallest collection of finite-arity partial functions of the natural numbers satisfying rather than 1 to 3, it's now 1 to 4. So 1, 2, and 3 are going to be exactly the same as before. So the partial recursive functions contain the basic functions we've already defined. They must be closed under composition. They are closed under primitive recursion. But in addition, they must also satisfy 4, which is closed under a further operation on partial functions called minimization. So 4, the remaining one to write down is this. So let me be consistent with my notes here. So if we've got a k plus 1 argument partial function in f is in curly, so little f, k plus 1 argument partial function is in curly f, the connection we're talking about, and then so is a partial function we call mu f, mu little f, that is. This is my attempt to Greek lowercase letter mu. So mu of f, which is a k argument partial function. So we're losing one of the arguments of f. Where mu of f is defined by, so we need to say what mu of f does. It's a k argument partial function. We need to specify what it does on the arguments little x1 through to little xk. And so what it does is it takes x1 through to xk, which is all but one of the arguments needed for little f. So we've got k out of k plus 1 of the arguments to give to little f. We then try to find the one missing argument for little f so that we get a 0 value by applying little f to it. And not only that, we try to find the smallest such, we're going to try to find the smallest value little x, such that if we apply little f to x1 through to xk and x, we get the value 0. So what it returns here is the smallest n such that applied to x1 through to xn together with n, sorry, xk, is 0. If such an n exists. And otherwise, if in the case, let me write that as an up arrow, meaning undefined. If no such n exists, then this is why we now have a, oh dear, otherwise. Next time I'll just write 6 a bit shorter. Anyway, so if we don't have such a, of course, there may not be any n such that the partial function f applied to it is 0. In that case, the minimization is undefined. So we're searching for a value, basically. It's a search thing. Now, I haven't quite completed the definition here, and there's a reason for that. So let's say we want this to be a computable operation. We've assumed that the function f is computable. We want this to be computable. So how would we try to compute this? Well, we want to find the smallest n such that this equality holds. So obviously we're going to apply f to this tuple of arguments together with 0 first and see if that holds. And if it doesn't hold there, we'll apply it to 1 and then see if we get to 0 then, and then to 2. We'll keep on going. And if there's no 0, well, we'll keep on going forever. And that's okay because the value is undefined, so we don't need to return a value. There's an issue to the search, which is f's only a partial function, so it may be given by an algorithm that goes into a loop. So what happens if we apply little f with n equals 0 and we go into a loop? Still, there might be some high-end value of n on which f's defined, but how are we going to jump? But do we want to jump out of the loop? We don't want to jump out of the loop and look for a higher value of n, because we can't safely jump out of a loop because we never know if that loop's just a temporary loop and it might eventually return a value. So actually, this is not a complete and correct definition of a function yet. We need, in order to make it computable, we can only find such a 0 if f is defined on all strictly lower n as well. So basically, if f is defined and is non-zero on all strictly lower n, that's okay, because then we can certainly find the value for f applied to 0 as its last argument, for it applied to 1 as its last argument, all the way up to n minus 1. We've seen those values, they're not 0. We know to go on to the next value, and then in the end, we find the value for which it's 0. So the actual requirement is we return the smallest n such that this holds, and f x1 through to xk n is defined for all n strictly less than n. Okay. In which case, if it equals 0 and it's the smallest n and f defined on all strictly smaller m, then the values on all strictly smaller m must necessarily be non-zero. But we don't need to put that in the definition because it follows. Okay, and this is called. So we had a name for all the other operations. This one's called minimization. And that's it. So the first theorem we had about the proposition we had about the primitive recursive functions was that they're total, they're all total. Just by its definition here, we suspect you would very strongly suspect that once we throw minimization in, the functions are not necessarily total. In any case, if these partial recursive functions are going to agree with the computable partial functions, we better include some non-total functions. So let's just do an example. Partial recursive function. And I'm just going to give a very simple example, just So we've already defined addition as a primitive recursive function. So clearly any primitive recursive function is partial recursive because we've given ourselves some extra power over primitive recursion. We've added one more way of combining functions for the partial recursive functions. So our H1 addition is primitive recursive, so prim rack, hence partial recursive, par dot rack. So that's so H1 is a 2-argument function, total one. So let's just consider what happens if we minimize H1. So apply mu to H1, so that's now a 1-argument partial function. So then let's call this, well, let's just call it mu H1. So mu H1 applied to the value x is going to find the smallest y such that H1 of x comma y equals 0 and undefined if no such y exists. So that's from the definition here. Notice I've omitted this requirement that the value is defined on all strictly smaller values. That's not needed because H1 is a total function anyway, so of course its values are defined on everywhere. You don't need to assume further the values are defined. But this is just obviously seen to be, well, H1 is addition, so the smallest, this is right, the smallest y such that, so this is the smallest y such that x plus y equals 0. We're searching through the natural numbers, and x is itself a natural number. So in the case that x is 0, the smallest such y, and indeed the unique such y is 0. And in the case that x is greater than 0, then of course there is no natural number y such that x plus y equals 0. So this partial function, it's a very uninteresting one, but it is at least a genuinely partial function. It takes the value 0 if x equals 0. So this is a partial function mu h1 applied to x. It takes the value 0 if x equals 0 and undefined otherwise. So the word of x is greater than 0. And did I move the board, the camera? No. Okay, so anyway, that's this definition of the partial recursive functions, a very uninspiring example of a partial function that's partial recursive, but nonetheless, at least it's one example. Maybe the exercise classes next week will contain some more. I'm not sure. I think we're mainly going to look at primitive recursive functions next week. But in any case, as we'll see in just a moment, there are, the power of the partial recursive functions is much more than it might seem at first. So I'm going to say the proposition and the theorem. The proposition is that simply every primitive recursive function is partial recursive. And I'm not going to, I've already stated that and the reason for it. So the partial recursive functions include the primitive recursive functions. The theorem is our main theorem for today, and what I want to do in the remainder of the lecture is prove it. I mean, not in full detail, because it's not a very nice thing to prove in detail, but the ideas behind the proof are interesting. And this theorem is the kind of major an example of a common phenomenon when one studies models of computation, that if one has a realistic model of computation that's not too weak, then it coincides with the notion of computability given by the notion of computability coincides with that given by the Turing machine model. So our theorem is the partial recursive functions coincide. So that's defined as the smallest class of partial functions closed under 1 to 4, as in this lecture, coincide with the computable partial functions, defined as in the last lecture using Turing machines. By the time you've completed lecture 6 and you've done your presentations, we will hopefully have seen many instances of similar theorems here. But this is, I mean, I guess for most of you, the first time you've seen some such equivalents like this. I think it's a really remarkable theorem because the definitions are so incredibly different. Turing machine is very much this little hardware with its computation steps and how it computes, and you encode the natural numbers using words and what you can do in manipulating words. Whereas the partial recursive functions as defined today is simply a collection of partial functions containing a few basic functions and closed under these 3 ways of combining functions. I mean, it's stunningly different, and it's really amazing that, I mean, what I find most amazing about this is that the notion of computable partial function as defined on a Turing machine has such a simple mathematical description. I think that's really the almost unbelievable aspect of this theorem. So we want to prove this. We want to at least understand why it's true to a relatively deep level. So there's a coincidence here. So we're going to actually show 2 inclusions. We're going to show that partial recursive functions are contained in the computable partial functions. That is, every partial recursive function is computable. And then in the other direction, show the other containers of the computable partial functions are contained in the partial recursive functions. So the first one, that every partial recursive function is computable, is not that hard. The idea is that the basic functions are computable, and the 3 ways we have of combining the partial recursive functions, the composition, primitive recursion, and minimization, all preserve computability. I will show you that argument in a bit more detail, but it's basically, it sort of fundamentally boils down to, you can imagine you can write a computer program for any of these partial recursive functions. That's another way of thinking about it. So anyway, we'll do that in the remaining part of this hour. And then in the last hour of the lecture, we'll do the other inclusion, which is that every computable partial function as defined by a Turing machine is partial recursive. And this is the difficult direction and the more surprising of the 2 directions here. And I'll talk about how we do that after the next break. Right. We want to prove one direction of this theorem, namely that every partial recursive function is computable. Proves that every partial recursive function is computable by a Turing machine. So the fundamental idea is that partial recursive functions are the smallest class of partial functions containing the basic functions closed under these three operations: composition, primitive recursion, and minimization. So we simply show that the computable partial functions are closed, also contain the basic functions, and are closed under the same operations. And then, because the partial recursive functions are the smallest such class, they're necessarily a smaller class, well, a class that's no bigger than the computable partial functions. So we show that the computable and are closed under 1 to 4. Well, the way I formulate it, I'm satisfied 1 to 4. And actually, to do this, I find it convenient to redefine the computable partial functions. So we already have a definition of the computable partial functions, but where we take the computable partial functions are functions computed by a Turing machine, where one uses for the k argument functions, the representation of the k product, of the k-fold product of the natural numbers, which takes binary representation separated by k-1 commas as the input. It's actually slightly more convenient to work with a different equivalent definition, which is where all the inputs are given on separate tapes of the Turing machine. So without bothering to establish the equivalence between the definitions, but that sort of thing is kind of already, we've passed those, we've learned to appreciate how that's done already for this course. We consider a function partial function from n to the k to n to be computable if there is a k plus 1 k Turing machine that takes binary representations of natural numbers x1 through to xk on its first k tapes input, and halts in the halt state with f of x1 through to xk on this k plus 1th tape whenever, well, let's say if and only if f of x1 through to xk. Tape, I of course mean with the binary representation of f of x1 to xk, so that binary word. Okay, so we've got a k plus 1 tape machine. K tapes are considered as the input tape, and the k plus 1 tape we use as an output tape. You'll see the reason that this is convenient a little bit later when we come to the proof. Anyway, we can accept that that definition is equivalent to for last week. And now we need to show that the basic functions are computable, and the computable functions, according to this definition, are under composition, primitive recursion, and minimization. All I'm going to do, I just want to give you a flavor of this, so all I'm going to do is prove that the computable partial functions, according to this definition, are under primitive recursion. The two interesting cases in the proof are primitive recursion and minimization. The basic functions in composition are pretty easy. So I'm not giving us the full proof, and also this part is only outline, but at least to give you some idea of how it's working. So show the case. That such functions are closed on the primitive recursion. And you like the other cases, you can consider them as being left as an exercise. But really, only the minimization case is of interest, really. So it is a relatively interesting case to think about minimization here. So I'm going to go to the other board to do this. Come on. So primitive recursion takes a k argument function little f, a k plus 2 argument function little g, and returns a k plus 1 argument function r sans serif r little f little g. So suppose, but of course these might be partial functions now, because we're dealing with the partial computable functions, the computable partial functions. So suppose f is a k argument function computed by k plus 1 tape Turing machine, which I'll call m sub f. So assuming it's computable, and therefore there's some, by this definition, this characterization, there's some k plus 1 tape Turing machine that computes it. And G is a k plus 2 argument function that's computed by now a k plus 3 tape Turing machine m sub G. We need to find a Turing machine. A Turing machine computing RFG. And remember, I just write it, I write the equations again in a box here so that we've got them to look at. So RFG is a k plus 1 argument function. But on 0 is f, applied to the other arguments. And on x plus 1, it's g applied to the other arguments, to x, and to the recursive call to RFG of x1 through to xk x. Again, it should be cleanly equalitous. And just put the arity here just to make it explicit. So this is the k plus 1 argument. Okay, so also we want to compute this. It's a k plus 1 argument function, so we want to give a k plus 2 tape Turing machine. But actually, to make life convenient, I'm going to give a k plus 4 tape Turing machine for it. And then we can reduce the number of tapes using what we did in lecture, I think at the beginning of lecture 2. So we define a k plus 4 tape machine for this. Which can be reduced to a k plus 1 tape machine it's in note 1, it was at the beginning of lecture 2, but I put it in note 1. So the idea about k plus 4 tape machine is we've got I'm just going to draw the tapes as single lines just to make it quicker. So the first k tapes are going to be the arguments x1 through to xk, 1 for each k, given in binary representations of the natural numbers. K plus 1, this is going to be the argument x. So the k plus 1th argument. The k plus 2 tape is going to contain a counter, which is going to be initially 0. The k plus 3 tape is going to contain the result of RFG on the previous iteration. And the k plus 4 tape is going to contain the result being computed. Okay, well, we now have the drawback of having the door open. But anyway, one can't live in a perfect world, so unfortunately, or maybe not, I don't know. Let's not get into philosophy. So this is a sort of schematic description of what the tapes do, but it's not very easy to understand because I haven't defined the Turing machine, so to speak, which I'm going to define at a high level, and I'm basically going to give the algorithm it uses to compute the function defined by a primitive recursion, like this. So the TM, so I'm going to define it at a high level, describe at a high level how this algorithm works. So the TM proceeds as follows. And the first thing it does, so it's given the arguments x1 through to xk and x of the function that we're giving to the function RFT that we're trying to compute. It's given those on the first k+1 tapes. So the next thing to do is to initialize the counter to 0. So we initialize tape k+2 to 0. Then we're going to use our Turing machine for little f. So our Turing machine MF. So the Turing machine we're defining is going to have the algorithm for MF in it and also the algorithm for MG, and combine them in the following ways. So it uses MF, the machine for F, to compute f of x1 through to xk, which are given on the k input tapes. The Turing machine for MF uses k+1 tapes, and we ask its other tape to be k+4 here. So using tapes 1 to k and k+4 for its output. And the point is that when k+1, when our argument x is 0, then f of x1 to xk is being put on tape k+4 and is the correct output value. So we're done. So step 3 is that if the numbers on tapes k+1, so that's the original argument x, and k+2, that's the number we've counted up to, and k+2 agree or equal, then halt with tape k+4 as output. So at this point, if just through going 1 to 3, if the numbers on tapes k+1 and k+2 are equal, that means that the k+1 argument, the argument x we gave, is equal to the 0 that we've initialized k+2 to. So that means the x is 0, and indeed we do want to return f of x1 through to xk as the output. Here, what I'm going to do, I'm going to put a looping point. So our Turing machine is going to loop back to this point. So this is like a label for computer language label for a looping point. And this isn't an instruction here, but I just want to say what's always going to hold when we get to this looping point. So at this point of the algorithm, tape k+4 contains the value RFG applied to x1 through to xk applied to y, where y is the current value on k plus 2, the value we counted up to. So this is like the loop invariant, if you like, for those who know computer science terminology. At every time we get to this point of the loop, our k plus 4, our value being computed, is going to be, we're going to iterate up RFG x is 0, RFG x is 1, RFG x is 2, until eventually the k plus 2 tape is the value x that we initially input, at which point we have the correct value on the k plus 4 tape. So all we need to do is, if we haven't done this, if the numbers didn't agree at step 3, then we need to go and perform the next step of the iteration. So how do we do that? Well, so step 4. So we found that the result on the k plus 4 tape is not the correct value we want to return. So at this point, it's useful to record it on the k plus 3 tape. So we copy the value on the k plus 3 tape to the k plus 4 tape to the k plus 3 tape. We then want to compute the next value of RFG for x plus 1. So we've got on our k plus 3 tape, we've got the current value, RF, which is this one. And to compute the next value, we need to apply G to x1 through to xk to x and to the previous value. So we apply mg to tapes 1 through to k plus 1, sorry, k plus 2, which is the current value of the count, which is the current value of the counter, and k plus 3. Now, the tape for G, the Turing machine for G is a k plus 3 tape Turing machine. Here we're only using k plus 2 tapes. But the other tape is these are the input tapes for G, and the other tape is the output tape. And so here we want to return the output on k plus 4. And the reason for copying the k plus 4 tape to the tape k plus 3 is because we don't know how the Turing machine for G is going to work, and we couldn't ask it to. Well, anyway, it needs its input on a different. The way I define things, it needs its input on a different tape from its output. Anyway, having done this, so once we've done this, we've got the next value of RFG on the k plus 4 tape. We can now increment the counter and then go back to the loop. So 6 is increment tape k plus 2, and 7 is go back to loop. That is the end of the description, and it's exactly 4 o'clock, so it's appropriate time to have a break, and we'll start again at 4:15. Okay, let me pause the recording. Resuming recording. Okay, so just before moving on to this part, so thank you for pointing out the mistake. There was a mistake on the board in the description of the algorithm in the loop part. It should have said that the tape k plus 4 rather than the tape k plus 1 contains this value. So to correct your notes. The other thing I should have told you, so there were these LaTeX notes for the course. I promised at the start of the course to tell you when there are things that are not in the notes. So actually, I should have told you that that description of the algorithm for this Turing machine is not in the LaTeX notes. Everything else today is in the notes, but this bit and that whole proof of closure and closure of the computable partial functions under primitive recursion, that's not in the LaTeX notes. Anyway, hopefully some of you have. Anyway, you can look at the video to get the details if you missed anything. Right, but now what we want to do for the last hour is turn to the other direction of the main theorem today, and that's the harder direction. That's to prove that every computable partial function, namely every partial function on the natural numbers that's computable according to the Turing machine definition of computability, is a partial recursive function. So it's contained in the smallest collection of partial functions that contains the basic functions and is closed into these three ways of combining functions: composition, primitive recursion, and minimization. If you think about it for a while, then you'll realize essentially the only way we're going to be able to prove something like this is we want to prove that every function computed by a Turing machine is contained in the smallest class, containing these basic functions closed under these operations. The only way of doing it is really to show that you can simulate Turing machines in an appropriate sense using partial recursive functions. So we're going to have to define suitable partial recursive functions that simulate the workings of a Turing machine. That's going to be a little bit complicated, so I'm going to give what I think is an appropriate level of description of that. And the first thing we're going to do, well, Turing machines are complicated structures. They have sets of states, alphabets, transition relations. Then when they compute with configurations, and these configurations involve tapes and words and head positions and things like this. If we're going to encode the workings of a Turing machine using partial recursive functions, we're going to have to encode all this information as numbers. So what we need to begin with is some sort of toolkit of methods for encoding interesting data, if you like, as numbers. So I'm going to spend a little bit of time doing this. So encoding data as numbers. Last week we were doing representations. That was about encoding data as words, in particular encoding numbers as words. Now we're kind of encoding everything as numbers rather than words. So the first thing I want to look at is pairing. This is quite easy. Essentially what we're going to do is we're going to assume we've got things encoded as numbers and look at how we encode interesting operations on things encoding as numbers. So one interesting operation on data is taking two data types and then considering the product data type or the data type of pairs of things. So we want to pair items of data as numbers. And we're going to do that. So the crucial thing we use is a pairing function on numbers. So I'm going to define a function from n squared to n, which is a pairing function, and the one I always like to use, so I've used this in other classes that some of you may have taken, is the function half x plus y times x plus y plus 1 plus x. We may recognize that this computes the sum of the numbers from 1 to x plus y. Is that right? I hope so. Anyway, if we look at what this does, if we've got x here and y going up here, so we're 0, 1, 2, 3, 0, 1, 2, 3, and so on. Well, it maps x, y, 0, 0 to 0. And then it starts counting down the diagonals. So we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, anyway, and so on. This should be a straight line. Anyway, it's doing that, and what we see from that is that P is a bijection from n squared to n. That's just simple mathematics. But more interestingly, well, we've defined already addition and multiplication as primitive recursive functions. Doesn't take that much of a leap of the imagination to see that this sum, including the division by 2, which always works because one of these numbers is even, that's going to be primitive recursive. And in fact, this whole function is primitive recursive. So we're going to see proofs of things like that and do proofs of things like that in next week's exercise class. But P is primitive recursive. And moreover, the projection functions, which are not easy to define in closed form. So the projection functions are, so let's put bullet points here. The projection functions, which I call here Q1 and Q2. Q1, Q2, which go from n to n. And they define that Q1 of the pair, we think of P as a pairing function. So Q1 of the pair x, y, any paired number is always x. And this completely defines behavior of Q because P was a bijection on the, from pairs of numbers to numbers. And Q2 of P x, y equals y. So it's not easy to define these, in fact, maybe it can't be done. It's not easy to define these projection functions in a sort of closed form using arithmetic operations, but it's easy to see how to compute them by, say, searching or something like that. And these two projection functions are, again, primitive recursive. So one way of defining them, you can suppose we're given a number encoding pxy, well, then we can search for an x value that will make this equation true. And then when we find it, or we need to also search for the y value, when we find the x value, we return that value. We can search that. You can imagine that can be encoded using minimization. But minimization is not one of the primitive recursive functions, one of the operations for primitive recursive functions. But actually what it can be done is it can be encoded using a bounded version of minimization that's always guaranteed to return a value. So you can define that in various ways, and one of them will be, I guess, addressed in the exercise class next week. And some sort of bounded search like this, it is an operation that can be defined on primitive recursive functions. Anyway, all we need is that these are primitive recursive functions. So taking a number, so that a Q1 takes a number, considers it, asks the question, which pair does it represent? And then give me the x coordinate of that pair. And Q2 is the y coordinate. Okay, so that's pairs. We're also going to encode finite sequences of numbers. So to give you an example here, so e.g., my encoding of, I'm going to use an encoding function that I'm going to use this kind of angled corner brackets for. And I'm going to encode a sequence of numbers. So let's separate them by commas, just so it doesn't look like one. So it doesn't look like 1,301, but it looks like the sequence of 4 numbers, 1301. So this I'm going to define to be the encoding the number that's given in binary as read the first number here, which is 1, and count from the right of your binary representation, we call the first digit 0. So we want 1. So we put the 1, we count up 0, 1, and we put the 1 when we get to the number we counted to. So we've got 0, 1, and now we go to the left of that 3. So we're going to go 0, 1, 2, 3. We put the 1 here and zeros to fill in. Okay, we counted 0, 1, 0, 1, 2, 3. Next one 0. So 0 is the next position, 1. And now 1. So we count again 0, 1. Okay. So if you like,
The numbers of 0 between ones.
yeah. So if you like, you have 1, 0 here between the 1. Right. So I was exactly going to say that. So we've 1, 0 here. Sorry, 0. No, 1. 1, 0 here. 3 zeros here. 0 zeros here. And 1, 0 here. And they're reading in this direction. Okay. So 1, 3, 0, 1. Oh, yes, well, one reason is it can be given quite a nice formula. So a word of numbers, W, is encoded as the sum from I equals 1 to the length of W of 2 to the sum from j equals 1 to I of w of j minus I. Remember, I'm indexing w I consider of as w sub 0, the first character, up to w sub length of w minus 1, the last character. Anyway, it doesn't look very neat, but it works. Or perhaps a better, I've actually got this one above. Well, it either works or it's wrong, in which case you can correct it. I don't even want to think it through now, but let's do it this way instead. So this one, I actually meant to write this first. So a sequence of numbers n0 up to nk minus 1, so a sequence of k numbers, is represented as the sum 2 to the power of n0 plus 2 to the power of n0 plus n1 plus 1, plus 2 to the n0 plus n1 plus n2, oops, that's n2 plus 2, plus all this up to 2 to the power of n0 plus n1 plus nk minus 1, plus, so n1, then 1 plus k minus 1. And the encoding is a special case. The encoding of the empty sequence is 0. Anyway, there are actually many ways of encoding sequences of numbers and as numbers, but this is a reasonably good way of doing it. And the following properties hold. So again, this function is a bijection. This kind from the set of finite sequences of natural numbers to natural numbers. This function, so I write it like this, just to mean the function from words to numbers, is computable. But what does that mean? Because now we're talking about a function on arbitrary sequences. Well, it's computable in the sense of last week, given a natural representation or let's say V. There are many, but they're all equivalent. All the correct ones are computably equivalent. The natural representation of n star in the sense of last week. So actually, you're going to look at a representation of n star today in the exercise class. But let's put this in brackets because we don't even need this in the proof that follows. So I'm just remarking on this fact. What is relevant to the proof is that we can encode sequences of natural numbers, and the operations, crucial operations for manipulating sequences, are again primitive recursive. So there are actually more operations than I'm going to write down as primitive recursive, but the ones I actually need to refer to today, I'm going to write down. So the functions sigma, Greek little letter sigma for selection. So this goes from pairs of natural numbers to numbers, and L for length, which goes from numbers to numbers. Below are again primitive recursive. And probably I didn't move the camera. Are primitive recursive. So L of n is simply defined to be the length of the word that n represents. Or rather, let's write it in a simple way that since we've got a bijection from words to natural numbers, we can define what L does on the encoding of any word, and this defines it as a function of natural numbers, and this simply returns the length of the word W. And sigma, what it does, given a word W, so given an encoding of a word W and a position I, the idea is it's going to return the number in the word W at index I. So the first number in the sequence is at index 0, and there are numbers in the sequence all up to length of W minus 1. But of course, I might be greater than or equal to the length of the sequence in which there's no such number to return. So what we're going to do to make it a total function is we're going to return Wi plus 1 in the case that we're given a legitimate index. So if I is less than the length of W, and otherwise we return 0 if I is greater than or equal to the length of W. Okay, so in the case that we get a legitimate index, we extract the I-indexed number from the sequence of numbers and return it plus 1 in order to say, yes, we have returned a number at that index. And this is again a primitive recursive function. Okay, so we're unscrambling this encoding, so to speak. Okay. So this is all the ingredients we need. So now we can go to our main proof. I'm going to have to refer to my notes quite a lot here because I always find this little bit a bit hairy. So something's hairy if it makes it sort of hairs on your neck stand on end or something like that. If you're into a dangerous situation. So what I wanted to prove is. So prove that, well, by which I mean, of course, an outline proof. But anyway, just to have an appreciation of how it works, that every computable partial function is partial recursive. And for this, we're going to work with the original definition of computable partial function using single tape Turing machines, as in the notes last week, using the product representation, giving the k inputs on one tape and separating them by commas. So suppose f from partial function with k arguments is computable. In other words, what we mean, it's computable, so it's computed by a particular single tape Turing machine, accepting the k tuple of numbers as arguments separated by commas, is computed, I suppose it's computed by a single tape Turing machine F, with tape alphabet gamma, and gamma had better contain 0, 1, and comma, because those are used to represent the k tuples of numbers. And also it must, of course, contain the blank symbol. But it might have some other convenient characters in too. And state set Q, a finite set of states. And what we want to do is we want to show how we can simulate the whole execution process of M on any input tuple of words representing a k tuple of natural numbers, using primitive recursive functions for each step of the process, and wrapping the whole computation up into a single application at the end of a minimization operator applied to some primitive recursive functions. That's what we're going to do. So just to make things convenient, firstly, we're going to have to encode configurations of the Turing machine. So configurations are going to involve words over the tape alphabet. They're going to involve states, head positions, and so on. So let's at least code the alphabet and states first. So we've got numbers to represent those. So we choose injective, that's one-to-one functions. So what do I call them? R, for some reason. I've got no memory of why I call them R. That's encoding of symbols in the state alphabet. I'm going to encode them as odd numbers. And you can obviously find an injective function because there are only finitely many symbols in the state alphabet is finite. And S is going to be a similar encoding of the state space. So we'll map that an injective function into even numbers. I use odd and even numbers in order to keep the encodings of states separate from the encodings of words, so I know which one is which. So then consider any machine configuration. We're now going to encode a machine configuration. So consider any machine configuration. So going back to drawing Turing machines like we were doing in the earlier lectures. So a machine configuration will have its interesting part of the working tape, well, of the tape. Where the characters, well, everywhere else the characters are blank. Some of these might be blank, but all the non-blank characters are contained in the interesting part. We've got the head position in the interesting part, by definition, and it goes up to a sub k for some, we've got some long word over the tape alphabet that contains all the interesting parts of the tape, including the head position. And we have a state. Remember, these are the three parts of a machine configuration are tape content, head position, and state. And we encode this configuration C as an encoded sequence. And the way I do it is like this. So I'm defining essentially the encoding of C here. So again, I'm using angle brackets, but now, so angle brackets mean encoding, basically. This is not an encoding of a sequence, this is now an encoding of a configuration as a natural number. The encoding of the configuration as a natural number is defined actually as an encoding of a sequence, and the encoding of the sequence is we consider these K characters from the tape alphabet and consider the sequence consisting of their encodings. So their encodings are done, the tape characters are encoded using R. So we consider the sequence RA1, RA2, RA3, ... all the way to RAI-1. And then to record the head position, I insert the encoding of the state to the left of the position that the head is pointing at. So I'm going to put the encoding of the state here. So I'm using the encoding of the state both to record the state of the configuration and the head position at the same time. And then I'll continue the sequence with the encoding of RAI. So this encoding, this sequence is saying this, the head is looking at the character RAI, and at the same time in this configuration we're in state Q. And then we continue all the way up to RAK. That's one way of encoding the whole of the configuration of the Turing machine as a single number. And from the encoding of sequences, you can see that these numbers are going to get quite large. For any kind of reasonable Turing machine, you're going to get quite large numbers encoding the configuration. Okay. So once we've encoded the configuration as a natural number, we can now consider lots of functions that represent aspects of the computation of the Turing machine as functions on numbers. And I'm just going to assert to you that all these functions are primitive recursive until we get to the last one, which will only be not primitive recursive, but partial recursive at the end. And for now, it's just going to seem like, I mean, it maybe already seems a bit magic. How are these functions decoding sequences? How are they primitive recursive? You're going to get an appreciation of that from the exercise class next week. Now we're going to consider a lot more functions on natural numbers. We're going to look at many more functions on natural numbers, and I'm just going to assert without justification that you'll come to appreciate it more after the exercise class last week, that they really are primitive recursive functions. So that looks in focus. Whoops. Right. But this is the part that I need absolutely to refer to the notes to get it right. assuming the notes are right, of course. So the following functions are primitive recursive. We're going to gradually get more and more complicated functions that help us look at the execution of the Turing machine. So firstly, the step function. Which is defined to be step of the number x is defined to be well, the idea is if x is the encoding of a configuration of the Turing machine, not all strings will represent encodings of the configuration, but a legitimate encoding of a configuration must contain, for example, only one even number, and that even number must be one of the even numbers in the finitely many even numbers that represent states of the computation, and that's encoding the unique head position. But in the case that x is the representation of some configuration C, and what this means is after one step of computation, execution. So if we start off in configuration C, M of the Turing machine, M from configuration C, this is C, say, it will make one step of configuration. It actually does make a step of configuration, it doesn't halt at that point. It makes one step of configuration and goes to the next configuration. And then the step x of the step function returns, given the starting configuration, returns the encoding of the next configuration that the Turing machine goes to. And if the Turing machine doesn't go to a configuration, it returns 0. And the encoding, you can tell these apart because the encoding of a configuration is never 0 because the string is never empty, because you always have a head position. Yes?
Is there n prime or n?
Oh, right, very good. There is no n prime. So this is the execution of the machine n. So I'm making, yeah, it is. So I'm making a possessive out of n. So yeah, you know, how do they make a possessive in English by apostrophe s? Yes, so a good question. Yeah.
And the last state of the last string we get, the last x, the Turing machine also, step of that x is also 0. Right?
Right, no, so what happens, so if x, so step of x will, okay, right, so if as x you give an input, so I think the answer is yes, actually. If as x you give the input of a halting configuration of the Turing machine, then the step function will return 0 because there is no subsequent configuration. Is that what you're asking? Yeah, okay, very good. So following this, we have run, which goes from n squared to n, so 2-argument function, where run of the Turing machine, so run on configuration x with n is simply the n-fold iteration of the step function on x. So this means step of step of step of x, and let me just write that down. So step of step of x, where you have n steps. Right. We'll then extract a single argument function, extract of x, returns the number n. So the point of extract is if we give x the encoding of a halt configuration that has a binary representation of a number on the string, extract will return the number that's represented on the string. So the idea is at the end of running the Turing machine, we're going to have a binary encoding of the result of applying f to some arguments, and we want to get that number back. So we want to return n here if x is the encoding of a legitimate Holt configuration, which must start with its head at the left end of what's on the tape. So it must start S. So the head must be at the left, so it must start with the state of Holt number, followed by the encoding R applied to the word W, where, so here by R of the word W, sorry, this is the word, shouldn't be encoding around. So by R of W, I mean, actually the sequence R applied to W0 all the way up to R applied to W, length W minus 1. If W is the binary representation of the word n. So this is saying return the number n if we're in a halting state with the binary representation of n on the tape. And in this case, return 1. And again return 0 otherwise. It doesn't actually matter that sometimes n can be 0 first. And then we're going to have a halt test, which tests if we're in a halting configuration. Well, actually tests if we're in the halt configuration. So this is again function of natural numbers and halt of x, halt question mark, because we're thinking it's a Boolean. So we're actually going to use 0 as the truth value and 1 as the false value. So this is 0 again if x equals s halt. It's again the encoding of a halt state, a legitimate halt state. So the word length, the index w, length of w minus 1, the sum w. And false, so this is if there is a legitimate halt state of the computation of the machine and we'll return 1, so 0 means true, we're in a halt state, and 1 means false if otherwise. I said I was going to write Sitzer next time, so let's write Sitzer because it's shorter. And in it, from n to k to m. So extract and halt are about how to deal with the end of the computation. Init is going to set up the initial configuration that we want to run the Turing machine on. So init is going to take our the init is going to take our k inputs and set up the initial configuration of the Turing machine. So init x1 through to xk is going to give us the encoding of, well, the initial configuration. We're in the start state with the head at the left. So we're going to S of start, followed by R of binary x1, followed by R of comma, followed by R of comma, all the way up to R of the binary xk. And here I'm making a little, so the encoding of the starting configuration. So here actually the binary representation of the number x1 is actually a whole word, and R is my function that's just applying to characters in the tape alphabet. So here what I really mean is R applied to each of the characters, each of the however many characters there are in x1 in succession. So here we've got the So I'll just write that in green here. So this is, so really by this, I mean R applied to each of the characters in X1, in the binary representation of X1 in succession. Just to keep the notation reasonable, I wrote it like that. And finally, with 2 minutes to go, we have the coup de grâce, I suppose. That's appropriate to say. Anyway, the culmination of the proof. So all these functions over there, they were primitive recursive. And finally, and if you want to think about why they're primitive recursive, you can see it's going to be quite complicated to define some of them. But anyway, you know, this is clearly the right level of, well, I don't know the right level, but this is a level of detail which is possible to do in order to finish by 5 o'clock, which is in 2 minutes' time, because finally is then given by a function we can define explicitly using primitive recursive functions and closure also under minimization. F of x1 up to xk is, we want to see that it's a computable partial function, and it is because we simply apply the extract function to what we get by running we need to know how many times, so we want to run the Turing machine. So we need to tell the Turing machine how many steps we want to run it for. And to find that, well, we're going to use minimization to search for the right number of steps. So we're going to do minimization of the function that takes a number n to the halt test applied to run of n of what happens if we run the Turing machine on the initialized data. Okay, well, in my notes, I have four closing brackets at this point, so let's believe that. So that tells us the number of steps this tells us the number of steps we want to run the Turing machine for, and we want to run it on the initialized configuration. So it's quite an unpalatable formula, but basically it says search through the numbers, search through possible lengths of number of steps that we can run the computation for from the initial configuration until we find the smallest such number that leads to a successful hold state. If none exists, never mind, it's a partial function, so then it's undefined. But if we do find such a number that leads to a hold state, then we use minimization to find that number. Then we simply run the Turing machine on that number for that number of steps from the initial state, and then we'll get an encoding, from the initial configuration, then we'll get the encoding of the halt configuration from which we extract the number that is left on the tape. Okay.
There's one closing bracket missing.
Oh, there is. There are 3 brackets. I mean, in the notes, I'm not saying the notes are right, but in the notes there are 3 brackets at this point. So hopefully it's there. Right, good. 5 o'clock exactly by my watch. I'm going to stop the recording.